Hello, everyone. So today we're going to be talking about the basics behind our next unit, which is gases. So we've all seen and interacted with gases, right? We know the three states of matter. We have solids, liquids, gases. However, gases have a lot of their own unique traits to them that we're going to be covering throughout this unit. So just as a quick refresher, a gas is a substance or matter in a state in which it will expand freely to fill the whole container, having no fixed shape, like a solid, and no fixed volume, like a liquid. So solids are defined as having a set shape to them, right? No matter what container they're in, they're going to stay in that shape, have the same mass, the same volume. Liquids don't necessarily have the same shape. They can change their shape depending on what sort of container you put them in. However, the volume that they take up or the amount of space remains the same. Gases don't have either of those constraints. So gases don't stay in a set shape. They fill up their container just like a liquid would. However, they don't have a set volume either. So if you put some liquid into a water bottle, it only fills up however much liquid you have. The gas will fill up the entirety of that bottle. So gases have several key variables that we're going to be talking about, and all these variables are related to each other in ways that we'll see throughout the rest of this unit. The first one is pressure, which we represent with a capital P. And pressure is a force exerted by a substance per unit of area on another substance. So the pressure of a gas has to do with how quickly those molecules are moving around and bumping into the sides of whatever container they are in. So the pressure of a gas is a force that the gas exerts on the walls of its container. Gas molecules are constantly moving, and they don't just stop when there's a wall in front of them. They run right into that wall and bounce off. And that force from a molecule hitting the wall many, many, many times very, very quickly is what gives us internal pressure in a system. So the units that we use for pressure, there's many of them, but there's two main ones that we're going to be using throughout this unit. The two key ones are atmospheres, or ATM, and kilopascals, kPa here. There's also millimeters of mercury, or inches of mercury. If you look on the weather channel, this is what you'll see there. There's torr. There's pounds per square inch, or PSI. If you fill up your bike tires or your car tires, using a bike pump, what it's measuring is PSI for most bike pumps. Next up, we have temperature, which we represent with a capital T. The temperature we talked about is how quickly molecules are vibrating or moving back and forth. For gases, they're not just vibrating, they're quickly moving because they're not constrained to any other neighboring molecules. So for a cool gas, right, the molecules are moving relatively slowly. For a hot gas, or as you increase the temperature, those molecules move quicker. And when we're drawing pictures of this, we indicate how quickly they're moving using different length of arrows here. So you'll see the cool gas is a short arrow showing that it's not moving as quickly as the hot gas with a higher temperature and a higher kinetic speed here. We represent that with a longer set of arrows. So the higher the temperature, the faster the molecules are moving. So temperature units, there are three main ones, and we've seen these before, right? We have Kelvin, degrees Celsius, degrees Fahrenheit. Here in America, in our everyday lives, we use Fahrenheit. When you look on the weather channel there, it's going to give you temperatures in Fahrenheit. In science, though, and in most of the world, we use Celsius or degrees Celsius here. And we're going to use that a lot in this unit. However, when we're doing calculations for gas problems, we need to use Kelvin and always Kelvin. So we've been using primarily Celsius for temperature, but for gases, we always use the Kelvin measurement of temperature. And we'll talk about how to convert from Celsius to Kelvin in just a second. But the reason behind this is because Celsius and Fahrenheit, 0 isn't the coldest you can go, right? 0 degrees Fahrenheit, that's really cold. 0 degrees Celsius, that's the temperature that water freezes at. However, they can both go way down into the negatives. Kelvin is not like that. Kelvin, the coldest possible temperature, is 0 Kelvin. So because of that, we have a 0 scale. We have no negative values we have to worry about. Just like we have a 0 scale for volume and pressure, right? We can't have negative pressure. We can't have negative volume. If we can't have negative temperature using the Kelvin scale, that allows us to have these really cool relationships between all these variables that we'll be talking about in the coming weeks. So Kelvin is useful because it has a base of 0 and no negative numbers. So the relationship between 200 Kelvin and 100 Kelvin is actually twice the amount of temperature or heat energy that's there, whereas the relationship between 200 Celsius is not twice the actual temperature of 100 degrees Celsius. So we want that directly proportional relationship that we get by having a base 0 scale. So temperature conversions, I'm not going to give you any problems that have Fahrenheit in them anywhere. So we just need to know really how to go from Celsius to Kelvin and from Kelvin to Celsius. So lucky for us, these conversions are really simple. If we have Celsius and 1 Kelvin, which is what most of these problems are going to be, we just add 273 to whatever our Celsius temperature is. So say outside it's a nice 25 degrees Celsius. If we want to know that temperature in Kelvin, we would just add 25 plus 273. That gives us 298, which would be, seems really hot, right? It's almost 300. However, that's about 77 degrees Fahrenheit, which is just a nice day outside. To go the other way, from Kelvin to Celsius, we just do the opposite, right? We take our Kelvin, we subtract 273, that will give us our temperature in Celsius. These are the two that you're going to have to know moving forward. However, in case you're curious, to go from Fahrenheit to Celsius, that's a little more complicated. You take the Fahrenheit temperature, subtract 32, divide by 1.8. That will give you your Celsius temperature. And then you just do the inverse operation to go the other way from Celsius to Fahrenheit, meaning you do Celsius times 1.8, then take that number plus 32. It gives you your degrees in Fahrenheit. These are just for fun. You don't have to know the bottom two, but knowing how to get from Celsius to Kelvin and vice versa is very important. Next variable is the number of molecules. The amount of gas that we have is important when doing these calculations. When we're talking about the amount of a substance, we like to use moles as our unit, right? So we use N as the variable for moles, which we've talked about before, and you'll see that in our equations later on. But N is our variable, moles is our unit. And then for volume, which is a capital V, the amount of space the gas occupies, right? That's what volume is defined as. Our units are liters, or a capital L for measuring volume. So there are many different gases. Tons of different chemicals come in gaseous form naturally, and when you get up to a certain temperature, pretty much everything will evaporate and turn into a gas. We, when we're talking about gases, like to, at least for now, assume that they all behave what we call ideally, or that means that they follow this kinetic molecular theory of gases. So we talk about ideal gases during this unit, and that essentially means that there's no intermolecular forces in between them. That's more true for certain gases than others, but we just, for now, assume that it applies to all gases. So the basic tenets of kinetic molecular theory are as follows. First, the volume of gas particles is much smaller than the distance in between them. Let's say if we have, a bottle filled with gas, that doesn't mean that each individual gas molecule is stuck right next to each other, right? There's lots of room in between them because they're constantly moving and bouncing off each other. So that means that most of the volume of a gas is actually just empty space. It's not completely molecules everywhere. Two is that gas molecules undergo no intermolecular forces. The only energy in a gas is kinetic energy. So again, number two, the truth behind this varies depending on the substance that we're talking about. But for the sake of this unit, we're talking about ideal gases, which are gases that behave this way, meaning that there's no intermolecular forces, there's no attraction between the molecules, right? When they're moving, they just run in, they hit each other, they bounce off, they don't get stuck together. Gas particles are in continuous random motion. So gas is the highest energy of the three energy states, right? They have a lot of movement energy. They're constantly bouncing off each other. They don't just stop. right? You can slow them down a little bit, but eventually if you slow them down enough, they're going to turn into a liquid and they're no longer a gas. And even then they're still moving, right? So gas particles are constantly moving. Number 4 is that gas particle collisions, meaning when they hit each other, are completely elastic. So when we think of something that's elastic, like a hairband, right? When you stretch it and then let it go, it snaps back to its original position. There's no energy lost there. Same thing with if you have, say, a rubber or a bouncy ball versus like a cardboard box. If you throw the bouncy ball at the wall, it's going to bounce off with just as much speed, almost exactly the same amount of speed. That would be considered an elastic collision, right? The energy or the movement energy stays there. It's not lost. If you throw a cardboard box against the wall, it's going to bounce off a little bit, but mostly it's just going to fall down to the ground, right? That's because that energy in your throw, that instead bends the cardboard a little bit. That's where the energy is going. It's going to the deformation or to bending that cardboard box versus being maintained in the movement. So if the energy is not lost, if the movement energy stays the same, like with the bouncy ball, that's called an elastic collision. With the cardboard, right, where that energy from the throw goes into bending the cardboard and it doesn't keep bouncing and moving around, that's an inelastic collision. And you'll talk more about that in physics in the future. Number 5 is that the average kinetic energy is the same for all gases at a given temperature. So if any gas is at a set temperature, it's moving at the same speed. It doesn't matter what type of gas that is. Then lastly, we have what we call STP. So when we're testing gases, we like to do it under controlled conditions, and very often we'll do it under STP, which stands for standard temperature and pressure. And so that's the temperature and pressure at which most gas properties are tested. Again, pressure and temperature were 2 of the variables we talked about as being important and related to the other variables that we also discussed. However, we like to test gases at a set temperature and pressure. That temperature is 0 Celsius, which is also known as 273 Kelvin. And then that pressure, you'll often see 1 atm, right? But these are all equal in the different units that we have. So 1 atm is equal to 760 millimeters of mercury, which is equal to 760 torr. Yes, these are the same. Which is equal to 101.3 kilopascals, which is equal to 14.7 pounds per square inch. So these are just pretty standard pressures of our atmosphere on us at sea level. So we're experiencing, since we're pretty close to the ocean, about 1 atmosphere of pressure, which is about 14.7 pounds per square inch of pressure, which is about 760 torr, right? So these are the conditions under which we normally test gases. So if we see STP anywhere, that means our temperature is 273 Kelvin and 1 atm. And that's it for our background information. We'll be talking a lot more about the different gas laws in the coming days, but this is all just basic information that we need to know moving forward.